All right, so very excited to have our guest speakers here, Kortney Lull and John Harrod. And we're going to kick it off first with Kortney and then hand it over to John and then get into Q&A from there. So Kortney Lull is Vice President for Midwest Geothermal, a closed-loop geothermal installation contractor that serves clients across the country with their ground loop installation needs. She has been with Midwest Geothermal from the beginning and has been integrally involved with their continued growth and looks forward to continuing to support the geothermal industry across the country. She assists their clients and customers not only installation of the exterior ground loops, but acts as a steward for the industry, offering learning opportunities for architects, engineers, construction managers, and homeowners. Kortney serves on the board of the Michigan Geothermal Energy Association. She was a formal board member here at Green Home Institute, and most recently is the chairwoman of the board of directors for the International Ground Source Heat Pump Association, IGSHPA. And then right after her, John Harrod, green energy contractor, consultant, and writer based in Ithaca, New York. He started his career in energy efficiency in 2001 as an energy auditor. 2006, he found Snug Planet, award-winning insulation and heat pump installer. His articles have appeared in Home Energy Magazine and the Building Performance Journal. So with that, Kortney, if you want to turn on your camera, I'm going to hand it right over to you, and we can get moving forward. Thank you. Just so you know, you are muted. So.
Okay, there we go. Let's try that.
Yeah. Oh, and
okay.
We're seeing the note slide right now.
Of course we are. We went through this. How's that? Better?
Yeah, perfect.
All right. So let's talk about geothermal. Thank you for the great introduction, Brett. I'm super excited to be here and talk to everybody about, really, let's start with geothermal, the pathway to net zero. We'll just start from the beginning. So brief outline, we're going to go over what is geothermal and how does it work, types of closed loop systems, design of exterior ground loops. I won't touch much on open loop systems. Feel free to ask me questions, but I tend to stray from open loops only because they use a lot of water. The average house, if you're going to go with an open loop or pump and dump system, will pump about 1 million gallons of water a year, and that's a lot of water to displace. So we're really just going to focus on closed loop, but I'd happily answer anybody's question on open. So we're going to go over horizontal, vertical, pond, directional. Then we're going to talk about what can geothermal do for you, some common misconceptions, and then question and comments, as Brett said, we'll do after both presentations. So I promise this is the only slide that I'm going to read verbatim, but described as a ground source heat pump, a geothermal heat pump is a central heating or cooling system that transfers heat to or from the ground. So really, when we talk about heating and cooling as a whole, what we're talking about is moving heat from one place to the other, right? So in the summer, our space is warm, so we're going to move it to the outside. And in the winter, our space is cold, so we're going to move heat into the house. And we do that conventionally with natural gas, right? We ignite something, burn it. Where in this instance, we're actually going to use the ground as our source and sink, so depending on the season, and we're going to store that seasonally. So in the summer, all summer, heat pumps have been rejecting that warmer temperature to the ground to reuse for later. We're going to use it all winter. And then in the summer, we have cooler temperatures in the ground that we can pull into the home to cool it down. So there's multiple names for it. If you Google geothermal, some of the information you're going to get is about traditional steam geothermal. What we're actually talking about is ground source heat pumps, water source heat pumps, closed loop heat pumps, geo-exchange systems, earth energy. There's multiple names for them. Okay, so if we talk about where the ground gets its energy, so obviously the big bright sun gives us 100% energy, but as you can see, some of that energy is absorbed or reflected into other things, but 51% of that energy is absorbed into the ground, which makes it an awesome place to gather or store energy. So I'm going to touch briefly on the mechanics of it and what's involved with a heat pump system, a water source heat pump system. So this is the box. This is what replaces your furnace. We have an air loop. That air loop could also be a water loop if we're going to look at radiant in-floor heat. Then we have a small circulating pump, a refrigerant loop. This is where the magic of geothermal happens, but I'm not going to dive too much into the refrigeration cycle since this is a 101 introduction, but there's some great cool animated videos on YouTube if you want to learn more about the refrigeration cycle. And then we have the ground loop, which is what I install. And then we have the domestic hot water loop option, which is amazing for savings. So we talk about energy and what energy is being used. So we use a small amount of electricity. There's a compressor, which is this little orange guy represented right here. No different than the compressor and the air conditioner that you have outside. Then we have a little circulating pump. And then this is representing a blower. And as I said, again, it could be another pump going to a radiant system. But for every 1 unit of electricity we bring into the house, we use 3 to 5 units of electricity from the ground, which makes it hugely efficient. So this is a commercial building, but it's just representing what we're doing. So in the summer, when you're at 100 degrees outside, it's easy to see that we can cool with that 40 to 60 degree temperature. In the winter, though -40 is a very extreme example for us here in Michigan, we've gotten pretty cold the last couple of years. But you can see to heat starting at 40 to 60 degrees is pretty darn easy. Okay, so path to net zero ready. So even if we don't go straight into net zero, honestly, geothermal helps a tremendous amount to get you to net zero ready. So most people don't know, but 65% of the energy that you use in your home is used to heat, cool, or preheat your domestic hot water or heat your domestic hot water. That's a huge amount of energy. So to really start down the path to net zero, that's the big nut you have to crack. And geothermal allows you to get there fairly easily. So then when you start to add things like solar and wind, taking care of your plug load and your electrical load, your demand is just so much dramatically less. It's pretty cool. So let's talk about installations, because this is the fun part where we have all kinds of cool pictures. So really, we have horizontal slinky standards. So these are open trenches cut in the ground, but pipe is buried. Vertical, we're bringing out a big drill rig to drill straight down. Saves a lot of space. Horizontal takes up quite a bit of space in real estate, where vertical, instead of going out, we're going down. Directionally drilled, you've probably seen directional drill rigs on the side of the road installing utilities. Same drill rig used here. Pond loops. Pond loops are cool. Pond loops are fun and cool to install, but there's a lot of rules to them, but they're great when we have an opportunity to do so. So let's look at some pictures. Slinky systems. So this is an example of a school actually in the Kalamazoo area. They were able to put in a slinky system under all their playground equipment and soccer fields, space they're not going to build on. So when we talk about a horizontal system, we say treat it a little bit like a drain field. Not because it's fragile, but we're telling you to do that because when you drive over something, you're driving temperature and moisture into the ground. Well, that gives us a little bit of unpredictability as far as being able to anticipate what we can use the ground for. So really, when you're talking about a horizontal system, it's great under areas that you're not going to build on. So in residential applications, we've done it under backyards or horse pastures or any number of areas where people won't build, but that they use for other things. So in the school instance, they're using it under playground and soccer fields, which is pretty cool. So this is an example of a horizontal open trench for a residence. An average home will need about a 500-foot long trench. Doesn't have to go in a straight line. As you can see from this picture, it zigzags back and forth, but those zigzags need to be 15, 20 foot on center so that we're not interfering with the energy we're exchanging. Because remember, we're creating a battery in the ground. So if I try and use the same battery out of the same pound of dirt, it's not going to be as effective. So here's an example of a vertical loop. Vertical loops are what we see most often when space is a concern. So if any people here in Michigan, the Michigan State Capitol, I have pictures of that, is going geothermal. Here in Grand Rapids, we have pictures of the Kroc Center, 63rd District Court, a multitude of commercial buildings and untold residential buildings, homes have gone geo. We put vertical bores under the driveway. Vertical really gives you the flexibility of putting it virtually anywhere, which is nice. So this is an example. This is the Croc Center here in Grand Rapids, the Salvation Army Croc Center. This is a project that we did. I've got some cool pictures to kind of show how this project progressed, but this is actually a military project down south of Indianapolis in Indiana, Camp Atterbury, but you can see it's a bit messy, but once we're done, you won't know we were there. So this is an aerial view of that same project. So you see, you can't see any of that mud, any of that mess, but this is what it actually looks like underground. So all of these red X's to the left represent a borehole, and then you can see the distribution pipe as it goes to the different buildings. But you can see how unintrusive it is after it's done. No exterior equipment, nothing to maintain on the outside, everything's buried so they can use that space for whatever else they might need. This was the drawing showing kind of a picture of what we installed. That was a pretty cool project. So here's an example of a house. This is a house on Lake Michigan. One of their driving factors for going geo is they didn't want to hear exterior equipment run. Big, beautiful house on Lake Michigan. Why listen to a condensing unit or something else run when they need space conditioning? So we were able to come up, put the bores in, and they put this beautiful lawn right back. Here's another residence. I was able to take the Google Earth image while they were still building, so you can't quite see the driveway, but that is where the bores are, is right under the driveway, tucked away. Pretty nice and neat. So here in Michigan, I love this picture. We actually drilled through this at Kalamazoo College. No idea when we were drilling. We drill through formation after formation. These bores can be 300, 400, 500, 600 feet deep, depending on the application. But we don't know necessarily what we're drilling through. We can't really see below ground, but this is a perfect example of we drilled straight through a rock and had a perfectly round hole. It was cool. We were able to pull that out and donate it to a school. So another vertical system underneath a parking lot at a big university in front of their football stadium. So the Michigan State Capitol, super cool project where we're able to put bores underneath what they're going to restore as green space and serve the entire Capitol building. Pretty cool project right here in our state, and we are very proud to have been part of that project. This kind of showing that geothermal can literally go anywhere. This is underneath a museum out on the West Coast where we drilled right in between pylons and put 704 bores under this building. So environmental impact. So not only does that allow us to reduce our energy usage in our home, but there are environmental reasons to go geo. So a typical house will save an acre of trees or is the same as removing 2 cars from the road. There's cool websites. I'm sure Brett will have this presentation available for everyone to see these links, but it's great for the environment too. So we'll quickly run through, I think I'm getting close on time, but what can geothermal do for you? So unmatched comfort and reliability. I will tell you, I love it in my house. I actually have natural gas, but I went to geo because I like the comfort. Because geothermal runs at a lower temperature coming out of the unit, have better air exchanges more often, the whole home feels better. Even in the winter, it's not as drying. It just feels better. My whole family enjoys it more than we do when we've had natural gas forced air units. So again, because we're not igniting anything, there's no combustion. So there's no more carbon monoxide concerns. Any of those are just gone. Simple controls. It can be as simple as you want with a single thermostat in a unit or as complicated as you want using radiant systems or zone systems. With a multitude of delivery options, Geo can support however you would like to enjoy your home. As I mentioned, there's no outdoor equipment required. I built a big, beautiful deck on the back of my house. I want to enjoy it, which was one of the driving factors for us to remove our condensing unit and go to geothermal, was so that we can enjoy our outside space without having any ambient noise, which leads us into reduced noise pollution. Lower utility operating cost. It is more efficient because we're getting so much energy out of the ground for every unit of electricity we're bringing into the home or to the building. The operating cost is incredibly low. On top of that, it's consistent annually. You'll see very consistent bills every month. Lower maintenance cost. So again, when we're talking about a closed loop system, it's a finite amount of fluid that we're circulating through the loop. There's really nothing to maintain to that loop at all. The pipe in the ground carries a 50-year warranty from the manufacturer. So the economic life of that pipe, that system, that battery you've built in the ground, 100 years. At this point, we don't even know how long it'll last, but an incredibly long time, which is fantastic. Reduced equipment structures. So when we're talking about commercial buildings or mixed use buildings, no reason to have equipment on the roof if we don't want to. We can put it distributed through the building or in a small mechanical room, which reduces footprint requirements. Longer equipment life. This one is harder for everyone to quantify, but when we talk about geothermal systems, because they operate at a lower temperature, the equipment tends to last longer. There are heat pumps that are coming out of service that are 20, 30 years old that really haven't lost any efficiency since they were put in, which is pretty amazing. And then flexibility in design. Now, if you don't have anything on the exterior of your home, you can design and landscape however you'd like. So I'll briefly go through some quick common misconceptions. It's only 50 degrees under the ground. There's no way it can heat my building. Well, if we're starting at 50 degrees, that's an easier starting place than we have ambient outside temperatures in the winter of 20, 10, 0. But it is really that magic of the refrigeration cycle. So when you have a refrigerant line right next to a water line, and refrigerant's very reactive, when you have warmer water temperatures against colder refrigerant, the refrigerant reacts very quickly and then can heat or cool your space. Really, the technology, whether it's water sourced, which is what I'm doing, or our next presentation, which is air sourced, very much works like your refrigerator does, right? You put something warm in your refrigerator, there's a big refrigerant coil in the back. If you put your hand at the bottom of the refrigerator, it's rejecting heat. No different than a heat pump. In our water source instance, it's rejecting it to the ground so we can use it later instead of just rejecting it into space, which is nice. I'm sorry, I'm trying to get through these. It is run by electric. There's nothing renewable about it, is a common misconception where it's absolutely not true. We're using electric to circulate the fluid, to run the blower, but that's no different than any other system. But because the amount of energy we're able to draw from the ground, it's incredibly beneficial. So for more information, I am Kortney from Midwest Geothermal, and the Michigan Geothermal Energy Association or the International Ground Source Heat Pump Association are great resources. But if you have any questions, I will look forward to reading them in the chat or answering them afterwards.
Great, thanks, Kortney. I'm going to hand it over to John now with Snug Planet. And John, please do take us away. Thanks for joining us. Oh, and you're still muted for some reason. How about now? There we go.
Okay. Let's see. Can folks see that?
Yeah.
Okay, great. Yeah, so I'm John Harrod. I am a contractor based in Ithaca, New York, and I was just looking at maps today and realizing that Ithaca, New York is about the same latitude and the same climate zone as central Michigan. So there's a lot of overlap. The other overlap that was interesting to me is how much of there are parallels between the path that Dr. Brown was outlining and what we're trying to do in New York State. That we are also trying to get to very deep reductions in CO2 emissions and do it in a way that addresses not only environmental issues, but job creation and social justice and affordability. Just a little bit about me. I originally went to school as a biologist and thought I was going to be a field biologist. And then about 2000, my environmental studies led me to increasing concern over climate change, and I decided to take a different path entirely and go into energy efficiency. I became an energy auditor and helped start a company that did building envelope retrofits. I did hundreds of energy audits and also insulated many attics and crawl spaces. In 2006, I left that company and formed the company I'm at now, which is Snug Planet. We continued doing energy audits and envelope improvements. And that led us to kind of take these to their extreme in what are called deep energy retrofits. We got a grant from New York State to do very extensive retrofits on several old houses in our area. We took all the siding off. We wrapped the houses in foam. We replaced the windows. And then we measured the energy performance. And the thing that was interesting to me is that with the, in some cases, upwards of $100,000 that we put into these houses, we achieved deep energy reductions, but only about 70%. We dramatically cut heating and cooling, but that left us with all these other energy uses still there. And it also was just a lot of work. There was no way that we could make this kind of project scale up to the point that we could make deep and meaningful reductions in greenhouse gas emissions. And so that really led me to get interested in heat pumps and electrification. And what I've learned over the last several years is that this is really an affordable and scalable path to get to our climate goals, to do it in a way that has a lot of benefits for people's health and well-being and their economic situation. This is how we see the path to zero emissions going in New York State, and I think this is an approach that is being replicated around the country and around the world. Efficiency is the starting point. We need to reduce the demand for energy by doing things like insulation and air sealing, but also by installing energy efficient appliances and lighting. We need to replace fossil fuel equipment with electrically operated heat pumps, whether they're ground source or air source. And we need to transition our grid to 100% renewable energy. And those three steps can be occurring in parallel. And if we do those, we will be able to eliminate emissions from residential buildings. One of the articles that I think, if you're interested in this this strategy is worth reading is an article that David Roberts wrote for Vox. David Roberts is a very thoughtful commentator on energy and climate issues. And a point that he makes really well in this article is that if you install a gas furnace today, it's going to keep emitting carbon over its entire 15 or 20 year lifespan. But if you install a heat pump today, its emissions are going to drop over time as the grid becomes greener. We've seen dramatic reductions in the emissions per kilowatt hour in the New York State grid, and we're also seeing renewable energy growing much faster than any other fossil fuel-based source of generation. And I just saw an article the other day that the last coal-fired power plant in Oregon had closed, and I think we're down to one here in New York State. So this diagram just gives a very quick explanation of the operation of an air source heat pump. It uses the refrigerant cycle just like a ground source heat pump, except that instead of exchanging heat with the ground, we're exchanging heat with the outdoor air. And it turns out that even though that outdoor air might be very cold, there's still useful energy that can be captured by the refrigerant. On the low pressure side of the system, which is outdoors in the winter, you have refrigerant that absorbs heat from the cold air. It boils that refrigerant, and then that refrigerant goes into a compressor. The compressor raises the pressure of that refrigerant, and in doing so, it raises its temperature. And now that heat is available to be transferred into the house. The temperature of the refrigerant is raised to over 100 degrees Fahrenheit, and that heat can then be emitted into the house. And the refrigerant cycles around and around and around, absorbing heat from the outdoor air, releasing it indoors. And typically with a air source heat pump, you're looking at 2 to 3 units of heat for every unit of electricity you use. In the summertime, that process is reversed, and now we're absorbing heat indoors and releasing it outdoors. So they can both heat and cool, and they do so quite efficiently. These are a couple infrared thermographs that I took of the heat pump at our shop. On the right, you see the outdoor unit. We had ambient air temperatures pretty mild yesterday. They were about 40 degrees. And the air entering the back of this unit was about 40 degrees. The air leaving the front of the unit was 4 to 5 degrees cooler. So that heat is being extracted from that air. And you can see the indoor unit on the left emitting that heat, producing very comfortable 90 degree supply air. And this single head does a great job of heating our entire, it's about a 1,000 square foot office. So one of the things that, as we're talking about air source heat pumps, we have to do is counteract some of the negative impressions that are out there about air source heat pumps. If people have any familiarity with air source heat pumps, it's often with an older generation of equipment that was loud, it wasn't very efficient, its performance dropped dramatically as temperatures got below freezing, and so people often ended up relying very heavily on expensive electric backup heat. New cold climate heat pumps are a completely different experience. This diagram shows performance of one of the brands of equipment that we install. The gray line shows the performance of a standard heat pump, similar to that older unit that I showed in the last photograph. With those, their performance declines steadily as temperature drops, so that the more heat you need, the less they produce. And by the time you get down below 25 or 30 degrees, there's just not a lot of useful output, and you end up switching over to either a fossil fuel-based auxiliary heat or electric heat strips. With cold climate heat pumps, we are able to maintain our full output down to 5 degrees or below, and still to be extracting useful heat from that outdoor air at temperatures well below 0 degrees. The first models of this technology that were available in our area are similar to the ones that you see here. And they were called ductless heat pumps. You typically had an outdoor unit connected to one and sometimes more indoor heads serving each room. And so that's still our most popular application. I showed this slide earlier today, and someone pointed out to me that we'd taken this photograph right after an install. We had forgotten to remove, or we hadn't yet removed the window air conditioner in the house, but they won't be needing that anymore. This provides a very much quieter and more efficient cooling as well. These are sometimes referred to as mini split systems. Split means that you've got an outdoor unit that has the compressor, the outdoor coil, and the electronics, and then you have indoor heads inside the house. So this is a very common pattern, but there are also a lot more options available. In addition to different colors of high wall units, different styles, we have indoor heads that are picture frames where you can put your artwork in the picture frame, and the blower and the coil are hidden behind that. We have ceiling cassettes that you see in the lower right there. Those are ceiling mounted systems, so if you don't have available wall space, you can mount those right in the ceiling. Increasingly popular are what you see in the very middle and right below that, compact ducted units. These are air handlers, so they have ducts connected to them, but they're compact. They're just about 8 inches tall, so they can be installed either in a basement ceiling, or sometimes in a closet, sometimes in an attic, and they can serve a suite of rooms. In some cases, they can heat an entire small house. But I think the cold climate heat pump technology that's really going to help us scale is what you see on the lower left here, the ducted air handler. These are available up to about 55,000 BTUs, which is suitable for most reasonably well insulated houses in our climate. And they can be direct swap outs for an existing furnace and air conditioner. So you're taking advantage of the existing ductwork system. In some cases, you have to modify the ductwork a little bit to get the required airflows. But you, instead of having these heads all around the house, you have one central heating cooling unit, and you have the same distribution and same essential operation experience that you would with your old furnace and air conditioner. So there's a lot of benefits to going with heat pumps, whether they're air source or ground source. Decarbonization being the one that's it's what gets me up every day, and it's just exciting to go out there and every day we're shutting off gas meters and replacing them with all electric solutions. Energy affordability is a real issue, especially with some of the economic struggles that we're experiencing now. Folks that are either heating with electric resistance or expensive delivered fuels like oil and propane, especially if they're in the lower income brackets, are going to be spending a big portion of their income on heating their homes. And transitioning folks to heat pumps presents a solution for that. And we need to figure out how to do it in a way that's equitable and sets people up for long-term success in terms of the maintenance and the upkeep of these systems. But it is, I think, a real solution for the energy affordability issue. And these also offer big comfort improvements. In New York State, about half our current housing stock has just window air conditioners, and another 15% don't have any cooling at all. And as summers are getting hotter and more humid, and as people are spending more time in their homes, these become real concerns. We also can use these air source heat pumps to solve targeted comfort problems. For example, if you have a bonus room or an addition that isn't adequately being heated and cooled, air source heat pumps can be a very cost-effective solution for that. I wanted to do a quick comparison with geothermal. I would never want to say that air source technology is better than geothermal. I think they're both part of the solution, and different technologies are going to be appropriate for different situations. Some of the big advantages of air source heat pumps relative to geothermal are the lower initial cost. We can often do whole house retrofits for about half the cost of what it would cost to do a geothermal system. There's a lower site impact and external footprint, and let me just qualify that by saying that one of the things that was really great about Kortney's talk is that she showed the extensive ground disturbance that occurs that then all gets covered up, and you're back to a beautiful yard or a soccer field or whatever. Air source heat pumps can be installed without any site disturbance at all, and they're suitable for places where you can't get that drilling equipment in, for folks that don't have land associated with their house, townhouses and apartment dwellers and so on. So that's one of the trade-offs there. Air source heat pumps are very flexible in their application, depending on what's needed and the geometry of the house. We can work with houses that have existing hot water baseboard that don't have ductwork. We can do a mix of ducted and non-ducted solutions, and we can also do fully ducted solutions like the air handler I was talking about. One of the reasons that New York State has gone so hard into air source heat pumps is that it's a scalable. And what I mean by that is, if we're going to electrify all the households in the state and ultimately the country, we need a technology that we can install quickly with a workforce that can be trained to do it well, and yet not folks that require so much training and specialization that there ends up just being a few people that can do it well. And so we're really looking to build a workforce that's capable of installing these and doing them right, so that they work well, that they're efficient, and they last a long time. Now, there's places where air source heat pumps do not look as good compared to geothermal. They are less efficient. Kortney was talking about coefficients of performance of 3 to 5. Those are numbers that I think are, very conservative. I've heard, that some of our ground source heat pump installers are routinely, upwards of 4 in terms of their efficiency. Air source heat pumps are going to have lower efficiencies. You're typically getting 2 to 3 times the heat output compared to the energy that you're putting in. Now, the way that these things work is that there's a huge difference between having coefficient of performance of 1 and coefficient of performance of 2. There's a big jump of going to 3, but each time you go up in coefficient of performance, you're chasing smaller and smaller gains. So there's no question that geothermal is more efficient. At some point, you do start to get into some diminishing returns. And so it's just going to be kind of a question of what makes sense for your particular situation. I think that, the smaller the home, the better the better its insulation. Your 800 square foot or smaller tiny home, there's no question in my mind that that's appropriate for an air source heat pump. As you get into larger homes where your heating requirements and your energy costs are going to be greater, geothermal is going to really shine. And when you get into commercial scale projects, schools and campuses and so on, no question, geothermal is a fantastic solution. Air source heat pumps, their output does drop off steeply as you get into lower temperatures. To the very low temperatures, you're typically good down to around 5 or 0 degrees, but you will need some backup heat in areas where you're routinely getting temperatures lower than that. And I think a really valid point that Kortney talked about that I would echo 100% is that air source heat pumps do have a shorter life expectancy. In part because the outdoor unit is subject to outdoor weather, rain, snow, hail. We don't have the loops buried deep in the ground. All of the moving parts in a ground source heat pump are safe in the basement, where they're going to be subject to a lot less wear and tear from the outer conditions. So I guess the take home from this is that both these technologies have their place, and I think they're both going to be part of the solution as we look to dramatically scale up electrification of our housing stock. And if anyone ever wants to talk more about this, please feel free to reach out to me. My email's right there. And I think at this point, we're going to have a little time for questions. Thank you.
Yeah, thanks, John. Thanks, Kortney. We do have some questions. Kortney, I see you, for those of you who did ask some questions, Kortney went in and answered quite a bit of them in the chat. So that's good, because we don't have time to get them all. I do see one that came in that I think is really good for both of you. I'll start with Kortney. And, these are both fully electrically, powered devices, right? Ground source heat pumps, air source heat pumps, it's all electric. So what happens, in the wintertime when we have a grid outage and you're relying on electricity to heat your house? Kortney, what do you do?
So specifically, I'll address that when we talk about generators, because really that's what people are going to try and do, is they're going to try and pick up where they left off with a generator. Yeah. So I will agree, and I would assume John would agree with me as well. The biggest use of electricity when you start a heat pump, whether it's air source or water source, is that compressor startup. So I encourage people that when they size their generator or they're starting to talk about when things turn on, start your heat pump first. It is your biggest electrical draw is when you initially start it up, but after that, the draw is incredibly low. So I would encourage people, absolutely use a generator, but don't size it for that initial startup and don't size it for that continuous run of the backup. The whole point of a generator is to pick up where we left off. So one of the questions that they asked was about backup and including not just if the power goes down, but resistance. Personally, use something else as a backup if you're going to size it that way instead of the resistance electrical heat. That's crazy expensive. So, there's a plethora of other options. But as far as when the grid goes down, sizing a generator, that's my recommendation all day.
And John, anything to add to that?
No, just that in our area, we have a lot of rural households where they do have a wood stove, which is another strategy that you can have there for those times when, you do have an extended power outage.
Now, I want to add to this a little bit because, obviously folks going net zero, they're putting in batteries. Realistically, how long are you going to get off with a battery nowadays to survive in the winter with your system, Kortney?
That's a good question for a generator guy. And, we're talking about all of our electrical stuff. I know I am diehard excited to look at an electric car. But, that's the tough thing too. I would hope that most of us were smart enough to plug some of that stuff in early on. But if you're in an area where you're either natural gas or you could have a small propane tank, run your generator off. I know that's a bit of a swear word when we're talking about not using gas, but it is an easier way instead of just straight off a battery in a generator. Use other fuel sources to run that generator that'll give you a longer lifespan of that generator if we're out for more than a couple days.
Mm-hmm.
But really, whether it's geo and we're electrified, your forced air furnace also uses electricity to run your blower. So if you're off,
I thought you just pumped gas into that thing and it just kept
right? Yeah. So honestly, regardless of how you heat and cool your home, if the electric goes out, we're all a little bummed out, unless you do have, like John pointed out, a wood stove or something, a fireplace or something else in your home.
Great. This question was specifically for you, John, but I'm gonna hopefully give Kortney a chance because I think there's some opportunity here too. But what are you seeing for swapping out gas forced air furnaces for air source heat pumps in existing multifamily buildings?
Multifamily, we don't actually do a ton of multifamily work, but there's no reason that it wouldn't be a very good match. A lot of townhouses and so forth have small air handlers already, and are really a good match for a cold climate heat pump. For smaller apartments, the retirement homes and so forth, where folks are just having a 1 or 2 bedroom 400 or 500 square foot apartment, oftentimes ductless are a really straightforward solution for those houses. A lot of those retirement communities that we look at have electric resistance, so people are paying really high bills, and a single ductless head can make a big dent in that.
Great. And Kortney, retrofitting in urban areas, what can geothermal do it?
Yeah, it really depends on the application. As I showed that museum that's being built, we're in the basement. That's downtown LA. So it's not much more urban other than downtown Manhattan that we can get, or metropolitan really. So it can be done in all kinds of installation. It's just, when are we allowed to be involved in the process? I'll give an example. We did a project on the Kalamazoo Mall where they completely stripped the building down to the stud. The only thing left were I-beams. We actually drove a drill rig into the basement, towered the rig up in between the I-beams, and ran each individual bore to a header in the basement. So there is a plethora of options. And then you also look at district systems. There are campuses, and I think Toronto is now going into a district geothermal system, adding into parts of their city, where using district systems, when we're talking about places where maybe you're not doing that big of a retrofit, but cities and municipalities can really tap into that resource and sell it as a utility or a service back to their customers.
Great, and I assume plug and play, if there's existing ductwork in apartments, you can plug in.
100%.
Yeah.
Yeah,
Great.
the heat pump is the heat pump, whether it's air source or water source, they plug in so easily and they tuck in nicely into apartments, and you could actually put them in the hallway so that any maintenance can be done in the hallway instead of actually having to enter the apartment.
Great. Well, we are at our time. John Harrod, Snug Planet, Kortney Lull, Midwest Geothermal, thank you so much for joining us. I'll send some questions your way if more pop up here in a little bit, so take a look there. Otherwise, if you can join us during the networking session, come back, jump into the conversation. We'd love to have you. Thank you for your time. Take care.